part 4 of chapter 5 about separation. You have learned about the phase equilibriums, and then it's time to go to the equilibrium-based separations. The problems of equilibrium-based separations are solved by using phase equilibrium as well as material balance equations. As you know, material balance equations or materials balance determines quantity of each phase. One material balance equation is available for each component. Then, in the case of equilibrium-based separations, we could use the phase equilibrium or related relationship between phases. Phase equilibrium determines compositions of two equilibrated phases. One phase equilibrium relationship is available for each component present in both phases. So, by using material balance equations plus phase equilibrium relationships, then we could solve the problems. Here are two different situations for the separator. Let me start with the first one. We have 5 components in the feed stream, which is introduced into the separator. In this separator, also we should provide some energy for heating or cooling down or something like that. Then we could separate some parts of components in the feedstock from the other parts of the feedstock. In this case, we have two output streams, and this is the first one and this is the second one. And in the first one we have ABC, and the second one we have BCDE. The main target of this separator is to separate the B component from C component. The first stream is B dominant stream, and the second stream is the C dominant stream. The other thing, like A and D and E, are non-key components for this problem. Then we should think about some equilibrium between the phase 1 and phase 2 in terms of component B and component C. Let me analyze this process in terms of degree of freedom. How many variables are there? 5 input and 3 output number 1 and 4 output number 2. So 5, 4, 3. 12 independent stream variables are available in this problem. And if we know the information about the feed stream, including all composition of 5 components plus the feed stream rate, then I could say 5 specification for the feed stream. So 5 information are there. And also, how many components are there? 5. Totally 5. A, B, C, D, E. So we would have 5 different material balance equations. Therefore, degree of freedom is equal to 12 variables minus 5 specification for the feedstock, and then 5 material balance equation, which is going to 2. It means we need to have 2 phase equilibrium relationship of B and C between phase 1 and phase 2. Okay, then let's go to the second situation. In the first situation of separation, we use the energy as a separating agent by heating, by cooling, something like that. However, in this second situation, we have introduced another stream to the separator, which is the solvent stream. Maybe we are trying to extract some parts of B and C into the solvent. So let me analyze these extraction situations. How many independent stream variables are there? Or how many variables are there? Input 5, output 1, 4, output 2, 5, and then one more thing, solvent. So 15 independent stream variables are available in this problem set. Also, if we know the information about the feed stream, then we could say 6 specification from feed flow and composition. Also, how many compounds are there? A, B, C, D, 5 plus S, solvent. So 6 material balance equations would be available because we have 5 different compounds are there. So degree of freedom is equal to 15 minus 6 minus 6 is going to 3. 3 more specification is required for this problem. We could easily see that 3-phase equilibrium relationship between 3-phase equilibrium relationships from B and C and S between phase 1 and phase 2. So with this 3-phase relationship, phase equilibrium relationship, then we could solve this problem. Okay, let me explain about this technology. So I could classify the energy-based separation technologies into 2 sorts. The first one is the separation technology at which energy is used as a separating agent, like crystallization, evaporation, condensation, distillation. I have said about that in the previous slide. Also, materials can be used as a separating agent, like absorption or adsorption and extraction. Let me start with crystallization first. 2 ways of crystallization are available. The first one is cool down. In that case, solubility of desired product decreases with temperature. Then we could get some crystals in the saturated solution. The other way is heating, and for example, evaporation. The other way is heating, and by evaporating undesired volatile component, then you could crystallize the desired product. Here is the example 5.13. Process flow calculations with liquid-solid equilibrium data. Potassium nitrate crystallization. So we have 100 gram of feed stream, which is introduced into the equilibrium stage. In this feed stream, you have KNO3, 50 the weight percent KNO3. It means 50 gram KNO3, and also 50 weight percent of water. and the temperature of the feedstock is 80 Celsius degree. Then this hot, well actually warm or hot solution of the potassium nitrate in water is introduced equilibrium stage, and then we will cool down the temperature of the solution. Then we would have two-phase solution having saturated solution plus solid materials, so crystallization. Then the output stream is split into two streams, and the first one is the liquid and second one is solid. The mole fraction or mass fraction of the potassium nitrate in the solid stream is equal to 1, of course. However, we have no idea about the composition of potassium nitrate and water in the liquid phase, so we should calculate it. Let me check the degree of freedom. Input is two input, right? I mean the flow rate of K and flow rate of W. And how about the output? Two output and one output. So totally 5 freedoms are there. Restrict. We have the information on the feedstock. So two input specification are there, and then we have two materials, K, NO3 and water. So two mass balance or mole balance would be available. So restriction is 4. So degree of freedom is equal to 1. Where is the 1? Can you find it? Of course, this is based on the equilibrium. This separator method is based on the equilibrium. So we could have an equilibrium relationship between two phases. Then we could solve the problems by specifying this problem. Okay, you could use the mass balance equation or something. Then you will calculate the mole fraction and the amount of the corresponding materials. But if you have a phase diagrams, then you could calculate everything. So right now 80 Celsius degree, and then 80 Celsius degree at 0.5 the weight percent KNO3 here. Then when you decrease the temperature, so this point is moving through the solubility curve, and then finally reach the two-phase region, from one-phase region to two-phase region. And then this point is split into 2 points. One point is on the solubility curve, so this is about the solution, and the other point is going to the vertical line on 1 gram salt per 1 gram solution line. It means solid of KNO3. So let me read the mass fraction. So for the saturated solution, then the 0.24 mass fraction of potassium nitrate in liquid. However, on the other hand, then how about the mass fraction of the solid? So this is just 1, right? Of course. Then from the value of KNO3, then you could calculate the the mass composition of water, like that and like that. And then let's go to the inverse level rule. This length is responsible for the solid, and this length is responsible for the saturated solution. So this line occupies 34% of total amount. It means the 34% of 100 gram is going to the solid. So the mass of solid is 34 gram, and 66% of 100 gram is going to the liquid by the inverse level rule. So ml is going to 66 gram. So right now you have calculated every composition and the amount only by using the phase diagram. Of course, you could use the mass balance equations. Here is example 5.14. Entrainment effects in equilibrium-based separations. Separation of benzene and naphthalene by crystallization. The title of this example is a little bit wrong. Entrainment effects cannot find in the equilibrium-based separations. Actually, in mechanical separations. I'll explain about that. So here, 1000 kilogram per hour of a liquid solution of 60 weight percent naphthalene, 40 weight percent benzene at 80 Celsius degree is cooled to 10 Celsius degree. So as you know, at room temperature, naphthalene is solid and benzene is liquid. The mixture of naphthalene in benzene at 80 Celsius degree would be a one-phase single phase solution where the naphthalene is totally dissolved in benzene. And then we have cooled down the mixture to 10 Celsius degree. Then the single phase liquid is split into two phases. One is naphthalene solid, and the other thing is saturated solution of naphthalene in benzene. The resulting solid and liquid phases are separated in a rotary drum filter. So let me think about the detailed process. At the very first time, we have a cool down process. So 1000 kilogram feed total is introduced into the cooler having 68%, 48% nitrogen and benzene respectively at 80 Celsius degree. But inside of cooler, the temperature is going down to 10 Celsius degree. At the output stream of the cooler, we have two phases, and this two-phase mixture is going to the rotary drum filter. So let me explain about the rotary drum filter. Here some feedstock is there, and there is some solution colored by blue and with some solid materials colored by yellow. And here is the drum. At the center of the drum there is some central duct, and the mixture is sucked toward the central duct. Of course, on the surface of drum we have a filter, so only liquid part is sucked into the central duct. Then on the surface of the drum we could find the filtrate or some solid material films. This drum is rotating, then the film is accumulated and then to the solid product stream. By using the knife, the film of solid filtrate is gathered toward the solid product stream. That is the rotary drum filter, which is the mechanical separators. So we have two units. The first unit is the equilibrium based separator, and then the second unit is mechanical mechanical separators. Entrainment happens on this second unit for the mechanical separator or rotary drum filter. So that is the situation. The process operates at a steady state, and your job is to determine how well the drum filter is performing. I'm saying about the entrainment. You determine that filtrate liquid flow rate is 505 kg per hour. So this filtrate liquid flow rate was given to you at 505 kg per hour. Without entrainment, maybe you have higher values of the flow rate. However, right now, after some entrainment, you have 505 kg per hour for the filtrate liquid flow rate. So by using some mass balance equation or something, how much entrainment does the filter leave? So some of water is remaining on the solid film on the drum surface. That is the entrainment, right? By how much does any entrainment changes the recovery of naphthalene in the filter cake product while the purity of the product. Okay, so flow diagram I have said about that, and we will use the phase diagram about the benzene and naphthalene. You have met this same phase diagram before already. So 80 Celsius degree, we are around here, and then this point is on the single phase region, having unsaturated solution of naphthalene in benzene. However, when this point is going down to 10 Celsius degree, you would have saturated solution plus solid naphthalene. Then you could calculate some composition for liquid and solid phase plus the amount of each phase. So let's go to the unit about the cooler first. And so you don't need to think about material balance equation. Of course you could use it, but everything is on the phase diagram. Okay, then right now, okay, so in this phase diagram, we should use mole fraction of naphthalene on the x-axis, and in the previous slide we have calculated the mole fraction of naphthalene from the mass or weight percent of naphthalene and weight percent of benzene already. That was the 0.478 naphthalene. So we are on here, and then the composition of the solution is this one, 0.2. How about solid? Of course 100%. So on this stream after cooler, we have easily read the compositions for the liquid phase composition of naphthalene in liquid, 0.2. I have said about that. And of course, how about benzene? The rest, 0.8. How about the naphthalene in solid? Of course 100%. Benzene in solid, 0. Then the next thing we should calculate is the amount. So this length is for the solid, and this length is for the saturated solution. I'm saying about the inverse Leva rule. So This point 0.478 minus 0.2 is the length of this line, and then full length is 1 minus 0.2. So 35% is going to the solid and 65% is going to the solution. As you know, we have total kilogram mole for the mixture is 9.82. Therefore, 9.82 by 35% is going to 3.41 kilogram mole per hour for solid. And how about 65%? That is the 6.41 kilogram mole per hour for the liquid. For the liquid in this stream. Okay, so that's it. Then by using the phase diagram in temperature, mole fraction coordinates, we have calculated every information about the stream out of the cooler, and that which is introduced into the filter. Then let's go to the filter unit. Here, so we know every information about the feedstock and the stream from cooler. Then it's time to calculate something for filter. So let me calculate the fractional recovery for perfect mechanical separation without entrainment. Then we will calculate the fractional recovery having the entrainment later. So we should check the amount of solid after filter, but I have said as of now I don't want to think about entrainment. Then it means in the final axis stream we have only solid, and the solid amount would be 3.41 before the filter, right? Because every solid content should be on the filtrate film. So 3.41 is going to 3.41. If you have some entrained liquid, maybe in this top stream you have some liquid having naphthalene, so the naphthalene amount would increase. However, if we don't have any entrainment, I have assumed like that, and then the numerator of the fractional recovery of naphthalene in solid phase is just 3.41 without any content of naphthalene in liquid phase. So numerator is 3.41, and the feed stream about the nitrogen. So total 9.82 kilogram mole per hour by the naphthalene mole fraction 0.478. Then 72.6% of feed stream is recovered after the filtration. So that is the value for the fractional recovery of naphthalene in solid. Then let's think about some entrainment. From the problem statement, the filtrate flow was fixed at 505 kg per hour. So let me change this mass flow rate into the molar flow rate. Then that is the 5.74 kg mole per hour. For the total flow rate of liquid in stream 4 or filtrate flow, the filtrate stream. Then let me calculate the entrained liquid amount above the filter. So liquid was introduced into the filter at 6.41. However, in the filtrate stream was found at 5.74. The difference is the amount of entrained liquid in the filter, right? Of course. So this is the entrained liquid in the filter. So 6.41 minus 5.74 is 0.67 kilogram more liquid per hour here. That is the amount of entrained liquid in the filter. Of course, this liquid has naphthalene in benzene. Then let me calculate the entrained amount per every kilogram solid in this top stream. So the numerator is related to the amount of liquid, right? So in these equations I have converted the moles into mass of liquid, and the denominator is the amount of solid part. So finally we could calculate the value about 0.135 kilogram solution entrained per every kilogram of solid in the top stream of output. Okay, so about 13.5% is the liquid, entrained liquid. Then let me calculate the fractional recovery of naphthalene with entrainment, and then I will compare this value is the value without entrainment. So the denominator is the same, the amount of the naphthalene which is introduced into this process. And the other thing is the amount of naphthalene in the top stream for output. So one comes from the solid. So solid is all naphthalene. So 1 by 3.41, and the other naphthalene comes from the liquid part. So total amount of liquid part is 0.67 kilogram mole per hour, and 20 mole percent of this stream is going to the naphthalene. The other is benzene. So this is the amount from the liquid part. So when compared with the fractional recovery for perfect mechanical separation, then the naphthalene value would increase or larger than the perfect separation, because we have more things there. That is the entrained liquid. So in this real filter having entrainment, we have higher values of fractional recovery, about 75.5% when compared with the 72.6% for perfect filter. Then you could calculate the purity for the top stream for output, and that is the 87%. So recovery increased with purity decreasing when with entrainment here. Evaporation, condensation, and equilibrium flash. Those separation processes produce vapor and liquid streams in equilibrium. Evaporation technique is used when a liquid feed is partially or completely vaporized. Condensation method is used when a vapor feed is partially or completely condensed. And the third one is equilibrium flash, which is used when components in the mixture have similar volatilities. A liquid stream is heated until some of it vaporized. Then the liquid and vapor phases reach equilibrium. Let's try to understand those separation methods by using some examples. Here is the example 5.15 about the condenser. So the situation is based on dehumidification of air by condensation. Here is a condenser, and the input stream is the air at 1000 kilogram more air per hour at 27 Celsius degree and 1 atmospheric pressure. This feed stream has some water. Then our objective is to remove the water from this feed stream. The composition of water or mole percent or mole fraction of water in this air is 2.6% or 0.026. The rest is of course air. This stream is introduced into condenser, and finally we have two streams. The first one is our target product, which is dry air. We have no idea about the flow rate, but the mole fraction of water should be below than 0.6% or 0.006. In the second stream, we have pure water. So the fraction of water is 100%. That is the situation. We don't have no information about the flow rate for dry air and flow rate for pure water in those two product streams, and also we don't have any idea on the temperature of condenser. So let's try to calculate those things. Of course, the amount of the product streams could be calculated from material balance equation in the absence of phase equilibrium diagram. Here we have two compounds or composite materials for the component for material balance equation, water and air. So we have two different material balance equations. The first one is for the air. So input is equal to output. Input in terms of the air, then 1000 kilogram more air per hour by its composition, 97.4%, is equal to output. We have two streams, but only in the top stream we have air. So let me calculate the amount of air in the top stream. Ng, I mean the flow rate for the dry air, is unknown with 99.4%. Let's go to the second equation, which is the material balance equation for the water. So input 1000 by 0.026 is equal to two streams. In both output streams, you could find water. So the first one, 0.006 with the dry air stream flow rate plus 100% with the water flow rate in the second output stream. Then we have two equations, unknowns 2 like Ng and Nl for the flow rate for two output streams. Then you could calculate the flow rate like that. The next thing we want to calculate is the operating temperature of condenser. So right now we have all information about the mole fraction and flow rate. The other thing is temperature for condenser. This process is going at 1 atmospheric pressure. It is fixed. To calculate the operating temperature, we will use the Raoult's law and Antoine equation. First, the saturated pressure of water is determined by Raoult's law at the given temperature and pressure. So this is the Raoult's law, and total pressure 1 atm and the mole fraction of water in the vapor phase was fixed at 0.06. Then also the liquid fraction in the second stream of water is just 100%. So we could calculate the saturated or the saturation pressure of water in the condenser. That is the 4.56 millimilli Hg. Then let's use the Untitled equation at the Untitled equation. What is the temperature to obtain this saturation pressure of water? So this value is given to this one on the left side of Untitled equation, and A, B, C comes from the appendix B for this water situation, and then temperature can be calculated. That is 0 Celsius degree. So this condenser should be operated at 0 Celsius degree. The last question is about the relative humidity of wet air. In the feedstock or feed stream, we have 0.026 mole fraction in air in terms of water, right? We should calculate the maximum water uptake capacity of air at 27 Celsius degree at this temperature. Then we could calculate the relative humidity of this wet air, which is defined as actual water vapor, like 0.026 here, and divided by saturated water vapor. So it is not the saturated situation. So let me calculate the amount of water in the saturated air in 27 Celsius degree at 1 atm. First thing, we could calculate the saturation water at 27 Celsius degree by using Untitled equation. So this is the Untitled equation at 27 Celsius degree. Then the saturation pressure is 1.427. I mean log saturation pressure. So finally 26.74 millimilli Hg is the saturation pressure of water at the air at 27 Celsius degree. This is the maximum value of this pressure of water. And right now, by using this saturation pressure, we could calculate the vapor phase fraction of water. This is the maximum value in terms of the mole fraction of water, or it can be considered as the water uptake capacity of air at 27 Celsius degree. So this is the Raoult's law again, and saturation pressure comes from the Untitled equation, and right now we are using the 1 atm or 760 millimilli mercury, and water composition is 1. Then 0.035 mole fraction of water is the maximum value of water uptake in air at 27 Celsius degree. Then, by definition, relative humidity of this wet air is 0.026. This is the present concentration of water. And 0.035 comes from here. This is the maximum value we could have water in this air. Then by 100%, then 74% is the value of the relative humidity of wet air in the feed stream. Example 5.16, which is about the equilibrium flash of a hexane heptane mixture. Here's the situation. In this diagram, I'd like to symbolize hexane as 6 and heptane as 7. The feed stream is introduced into flash drum at 100 mole per second as a total flow rate. In this feed stream, you have hexane 0.4 as the mole fraction and heptane 0.6 mole fraction. By heating this mixture, you will split this liquid mixture into vapor phase and liquid phase. Of course, we could get the vapor phase in the top stream and the liquid phase at the bottom stream. So also here, the temperature and pressure is given to you for operating flash drum. That is the 111 Celsius degree and 1520 millimilli mercury for the vapor phase and liquid phase, because those two phases are generated from the flash drum at the equilibrium state. That is the situation, and then we'll try to calculate the every variables for the output. So first, I'd like to calculate the degree of freedom. Maybe it is going to 0. What is the freedom? In this case, let me consider all variables in the output stream. So total vapor stream and total flow rate of liquid stream, NV and L, and Y6, Y7, and X6, X7. Of course, Y6 plus Y7 is equal to 1, but in this case, I have taken all of compositions as variables. And equation, the two material balance equation, because we have two compound and two equilibrium equations, which would be Laur's law, and two summation equations. Let me check it. Material balance equations here, you could do it. In is equal to out, and the summation equation here, and Laur's law is set up for hexane and heptane. Then we have 6 equations, so degree of freedom is 0. By using those equations, you could find all values of the composition and total flow rate for each stream. Of course, during the calculations, you should calculate the saturated pressure of hexane and heptane by using the Antoine equation. Here, 111 Celsius degree was used for calculating the saturated pressure. Then here is the result, and based on those values also you could calculate the recovery of 6 in the top stream and 7 in the bottom stream. So like 50% and 69%. That is the example for the hot flash drum. Another example, 5.17, which is about vapor liquid separations with non-ideal solutions. Equilibrium flash separation of ethanol water mixture. Let me check what kind of things happens there. A liquid stream as the feed stream containing 40 mole percent ethanol, E for ethanol, W for water, 60 mole percent water is fed to a flash drum operating at 1 atm. The feed rate is 100 gram mole per second, and within the stage, the temperature is raised to 85 Celsius degree. What are the flow rates and compositions of the vapor and liquid streams leaving the stages? It means we need to calculate all variables for output. This is very similar to the just previous example. Assume steady state operation. Then the operating temperature and pressure is 85 Celsius degree and 1 atm, something like that. And Fortunately, in this case, we have the phase diagram, which is different from the previous example about the hexane heptane. In the previous example, we didn't have a phase diagram, so we have used the mass balance equations or material balance equations. However, in this case, right now we have the phase diagram in temperature versus mole fraction of ethanol coordinates. Then we don't need to think about using the material balance equations. So what is the point we should have for these situations? At the flash drum, we are trying to make an equilibrium, which is set up at 85 Celsius degree. And also, the composition of ethanol is 0.4. So we are at here, and this point is split into 2 points. One point is going to the liquid part, and the other point is going to be to the vapor side. So from those 2 points, you could read the compositions. For the liquid phase, composition of ethanol is 0.13, and vapor or gas phase composition of ethanol is about 0.48. And also, the contribution of this length to the full length is about 77%. What does it mean? 77% of the mixture is going to the vapor phase, inverse leveler. 77% is going to this curve and vapor phase, and the rest, that is to say 23% is going to the liquid phase. Then finally you could also calculate the amount of flow rate for each streams. That's it. Distillation. This is the last separation technologies introduced in this chapter. Distillation is multiple equilibrium flashes. Distillation column is a stack of trays, each of which functions as an equilibrium flash separation stage. In this column of distillation, that is to say, equilibrium flashes to concentrate and separate more volatile and less volatile compounds are repeated through the column. Okay, here is the schematic pictures about the distillation column. We have several trashes or stacks here and there. Each stack is considered as equilibrium flash separation stage. Then let's go to the other pictures here, and we have a column here, and here are the 1, 2, 3, 4, 5, 6, 7 fraction outlets are there. Each outlet has its own product. Also, along these columns, we have some distribution of temperature. The bottom temperature is the highest, and the top temperature is lowest. Also, this temperature is defined the products for each fraction outlet. At the top, the product is gases, where the number of carbons is 1 to 4. The boiling point range is about 0 to 30 Celsius degree. Then from this outlet you could get some natural gas. The next one is naphthas, including gasolines. Number of carbons 5 to 10, and boiling point is higher than the first one, like 30 to 180 Celsius degree. Then kerosenes, gas oils, lubricants, fuel oil, and then finally we would obtain the asphalt. The boiling point of asphalt is the highest, like higher than 600, and each carbon number is longer than 80 carbons. This is the petroleum distillation. Let me magnify some part of the distillation tower, and here we have two stages, and liquid is going down or going out through the fractional outlet, and then vapors is going up. So smaller molecules are going up, and then the larger molecules are going down. That is the distillation tower or column, and which can be considered as a stack of trays, each of which functions as an equilibrium flash separation stages. Please click this link and you could enjoy some video clip for the distillation process. I have said the distillation column has several trays and the stages. So my question is that how many trays do we need to reach the specified specification or purity or recovery? Fenske equation is the equation to determine the minimum number of stages. So this one, it means the ratio of mole fraction of A to B in distillate or top product, and B and A for the bottom product. That is the separation factor for the entire column. For the mole fraction for this numerator, you will input the specification or your operation criterion for your process. And denominator, you could find the ratio of B, the saturation pressure of A and saturation pressure B. Let me try to understand the meaning of this one. The ratio of the saturation pressure here, A to B, and by using Raoult's law, this pressure ratio is going to the mole fraction ratio. Actually, this is the separation factor for a single equilibrium stage. Okay, so again, for the denominator, the value is going there as the separation factor for a single equilibrium stage, and the numerator value is about the separation factor we want to have. So if this number is larger than this number, we need to have more number of stages. So this ratio is going to the minimum number of stages. One more things. For calculating the saturation pressure in the denominator, please use the average temperature between top and bottom. So you could understand this equation from the next example. Example 5.18. In example 5.16, previous one, you analyze the separation of a mix of 40 mole percent hexane and 60 mole percent heptane using a single stage, in this case single stage flash column operated at 2 atm and 111 Celsius degree. The result was not impressive. The vapor was only 52 mole percent hexane and the liquid was only less than 70% heptane. It means we didn't have very high purity hexane and heptane from the single stage flash drum. So I'd like to use the multiple stage flash drums, which is so-called distillation column or tower. Your customer demands 99 mole percent pure hexane instead of just 52 mole percent, and 99.5 mole percent pure and hexane, which is much higher than about 70 mole percent heptane, which is obtained from the single flash distillation or single stage flash drum. You decide to design a distillation column to meet customer specifications, and you choose an operating pressure of 2 atm. This is 2 atm. Estimate the temperature at the top and the bottom of the column. About how many stages should be column have. So let me start the calculation. The target is 99 mole percent hexane and 99.5 mole percent pure heptane. As you know, hexane is more volatile than heptane, so that the top product is hexane and bottom product is heptane. Then let me try to calculate the temperature of obtaining 99 mole percent pure hexane at the top of distillation column. Hexane is more volatile than heptane, so that this temperature is not the bubble point but the dew point, right, for the top product. Dew means the vapor side rather than liquid side. For the dew point temperature, the given compositions like 99 or 99.5, 99, the given composition are the vapor phase compositions, right? Because we want to get the 99 mole percent hexane in the vapor. It means 1% heptane in that same vapor. So Laurent's law like that, and the vapor phase composition are fixed. So the summation of X, the liquid composition, is equal to 1. So X6 plus X7 is equal to 1, and these liquid phase compositions are converted to vapor phase compositions here, and Y6 is 0.99. 6 stands for the hexane, and Y7, where 7 stands for heptane, is going to 0.101. Then total pressure is going to 2 atm here, and saturated pressure for each species comes from the Untitled equation. Then this pressure variable is converted to the same temperature variable. Then you could calculate the temperature. The temperature of dew point is here 93.1 Celsius degree. This is the temperature for the top of the distillation column. In the same way, very similar way, you could calculate the bubble point of the bottom product of distillation tower. In that case, the given value of the composition is going to the composition in liquid phase, the composition in liquid phase, right? So X6 is X7 is 0.995, the rest is 0.005, and also pressure is 2 atm, and saturation pressure can be described by the function of temperature by Untitled equation in the same way for the dew point. Then find this equation is the function of temperature, only single temperature. That temperature is the bubble point for the bottom product, and the calculated value is 123.7 Celsius degree. And then it's time to the minimum number of stages. Before calculating the separation factor for this distillation tower, we need to calculate the saturated pressure for the single the stage of the flash drum. So for calculating the value about the denominator, we will use the average temperature value between the dew point and bubble point. So 93.1 and 123.7 is going to 108.4 Celsius degree. And at this temperature, you could calculate the saturation pressure for hexane and heptane very easily by using Antoine. Then that is the 1009. Then, no. For heptane 1009 and for hexane 2275. Then those value is going to the numerator, and also for the denominator, this value is going to the denominator. And how about the separation factor for this distillation tower to satisfy the customer demands? So we know the value about the composition, that put all of things here and there. Then finally we could calculate the minimum number of stages. Here 12. So we need to have 12 stages to satisfy the customer demand, like 99 mole percent pure hexane and 99.5% pure heptane. If you have used the single stage flash column, just we have obtained like the 52% or less than 70% hexane and heptane. So it means 12 stages means 12 the stages of this process is required for reaching the higher purity of hexane and heptane we want to obtain. That is the example for the distillation tower. Then here is the homework for this chapter. And finally, we have finished the chapter 5 about the separation. Please check the example 5.10 again. It is very important example. That's it for chapter 5.